Hi, this is Chris Good, and here's a lecture on repeated measures designs. Repeated measures designs. Repeated measures designs have several distinct advantages, mainly that because the participants are serving as their own controls, you gain a couple of these advantages, such as the fact that fewer participants are needed. So in a repeated measures design, you're actually using the same group of people for all the conditions of your experiment. That means that every person in the experiment experiences every condition that you create for the experiment. For example, in our Ginkgo study, we've got two conditions, Ginkgo and placebo. So we've been talking about this as an independent groups design where different people experience different people are taking Ginkgo than taking the placebo. If we did it as a repeated measures design, everyone would take Ginkgo, we'd measure their memory, and then everyone would take the placebo and we'd measure their memory again. So people serve as their own control group, and therefore you only need half of the participants, right? So you don't need a whole group of people to experience the other condition. You already have those people. The people who get the treatment are the same people who get the control. Because they're the same people, it actually makes it statistically easier to find a significant effect of the independent variable, if there is one there. And we call this statistically, we call it increased sensitivity. And the reason that we have it is that people are more different from other people than they are different from themselves at different times. So variability between people is usually larger than variability within people. So that between subjects variability that forms the denominator in the t ratio is going to be bigger than the variability within the same group of people within subjects. And so in the repeated measures t, you're going to be dividing by a smaller number. Remember, the denominator is our measurement of variability. When you divide by that smaller number, you end up getting a larger value for t, or let's say a more extreme value, because it could be in the opposite direction and negative, so it could be further away from zero in that direction. And that means that t is going to be more extreme. You're more likely to reject the null, and so you're more likely to find an effect of the independent variable. And the last advantage that you get from doing a repeated measures design is that you eliminate the possibility of individual differences confounding your study. It's possible that in an independent groups design, you might by accident assign more people with a better memory to the Ginkgo condition than to the placebo condition. That's not going to happen here because it's the same people in each group. So there's no individual differences to covary with your independent variable. They're the same people in each group. So lots of advantages to the repeated measures design. Unfortunately, there are also some significant disadvantages to this design. You might have already thought of one that, well, if people take Ginkgo and we measure their memory, and then we give them a placebo, the same people, and measure their memory again with the same test, they might do better the second time because they're getting practice, they're getting a workout of their memory. They're practicing the test. If you use the same test, then they've seen the test before, and that can be a problem too. So the order in which people experience conditions can be a confound, and if you don't know at the end whether it was the order of the conditions or the conditions themselves that changed the dependent variable, then you can't be confident that you've made that independent variable truly independent. That's a threat to internal validity, the extent to which you can be sure your manipulation caused any differences rather than some external variable. So the problems inherent in repeated measures designs we call order effects. So the possibility that the order in which you experience conditions can have an effect on the outcome of the study, that's what we call order effects. And there's two main types, carryover effects and progressive error. And there's two types of progressive error that I want to talk about. Carryover effects have to do with the effects of a condition that might persist into the experience of the next condition. Let's imagine that if you take Ginkgo first and it really does improve your memory, it actually might continue to work even after you stop taking it, so your memory's still really good when you take the placebo, and then you don't see a significant difference between those two measurements of memory, suggesting that ginkgo doesn't have an effect, when in reality it did have an effect that persisted into the placebo condition. And so you might obscure something. That's a carryover effect. Progressive error are order effects that affect subsequent measurement conditions, but they don't have anything to do with the treatment itself. So carryover effects are when the treatment has an effect. Some treatment in the condition, in one condition, has an effect that continues over into the next one. Progressive errors don't have anything to do with the treatment itself, but they have to do with the experience in that condition other than experience in the treatment. And what I'm talking about is what we mentioned before. If you do the placebo first and measure the memory, then the ginkgo and they measure the memory and it's better, is it because of the ginkgo, or is it because they had a chance to practice this memory test? Even if you use a different type of test, the fact that you measured it might affect subsequent measurements of it. So we call those types of progressive errors practice effects. You also might have people not do as well the second time just because they're tired. They're tired of participating in the study and they stop trying and they don't do as well. So if we do ginkgo first and we find that they get better, they do better than when they then take a placebo and you measure their memory, they don't do as well after the placebo, they might just not want to be in your study anymore and they stop trying. We call that fatigue, and it's the other type of progressive error along with practice. Those progressive errors, in addition to carryover effects, are together we just call generally order effects. The good news is that there's ways to control for order effects, and this has to do with people experiencing different orders of the conditions of your study. We call that counterbalancing. So we say that the order of conditions in a repeated measures study must be counterbalanced. The reason we have to counterbalance is to prevent order effects from happening, and I'm going to talk about two types of counterbalancing, complete and partial or incomplete, and I'm going to give you two examples of each. So I hope you can organize these by these two different main types. The first type of counterbalancing, that is people experiencing different orders of different conditions, we call complete. We call it complete because every participant is going to experience every condition multiple times. So everybody in any repeated measures study experiences all conditions. But in complete counterbalancing, in this first type, complete, every participant is going to get all of those conditions many times in many different orders, or at least in several different orders. So every participant gets all the conditions, and then they get all those conditions again in some other different kind of order. Partial or incomplete counterbalancing has to do with different participants experiencing different orders. Everyone experiences all orders, but different people experience the conditions in different orders. In the first case, complete counterbalancing, we say that we've balanced the order of conditions within the same participants. And in incomplete counterbalancing, we say that different people experience different orders. We say it's counterbalanced between participants. Here's one example of the first type, complete counterbalancing. It's called block randomization. We call the number of conditions K, so K stands for the number of conditions, just like N stands for the number of participants. In block randomization, we create blocks of K conditions, so if K is 2, you have 2 conditions. A block contains both of those 2 conditions. If you have more conditions than that, let's say you have 3 treatment conditions, then you would have a block of 3 conditions. In block randomization, we administer blocks of however many conditions you have. You go through all K of those conditions, and we give them in a random order, but then we do it many different times for many different blocks. For example, if K equals 3, and we do 18 blocks of 3 conditions, there's no rule to that, it's just this counts the number of trials that you get. 3 conditions presented 18 times in a row would give you 54 different trials of 18 blocks with your 3 conditions in a random order in each block. And the only rule is you have to complete a block of 3 conditions in some random order before you go to the next block. In this particular study that comes from Sackheim et al. In not 1078, but 1978, let's fix that, it was really cool. So this was actually done in the days before Photoshop, and the authors were interested in the emotional expressions that people make with their faces, and which side of the face is more expressive. Well, the central photograph you hear is the original photograph, and even before Photoshop you were able to go into the darkroom and sort of flip one half of the photograph and reverse it onto the other side. That's what they've done with the photos on either side of the center photograph. On the left side, you can see that the left side of this person's face, the person's left that is, has been mirrored, flipped in a mirror image over to the other side of the face. So what you're seeing in the left is 2 left-hand sides of the face. What you're seeing on the right is both right-hand sides mirrored, and what you see again in the center is the original photograph. I think that most people would agree that for this particular example, for this guy, he's trying to make a disgusted facial expression, and then it's more expressive when you view the left side composite, that's the picture on the left, than either of the other 2 ones, even the original photograph, suggesting that at least in this particular case, the left side of the face is more emotionally expressive. Well, in the original study back in 1978, they used a block randomization trial type. So in this, there's 3 conditions, so k equals 3. They did 18 blocks, and in each block, the 3 different types of photograph from many different types of emotional facial expressions was randomized. So in this first block, you can see trial 1, 2, and 3. The conditions of original photo, the left composite and right composite, that's O, L, and R, were presented in a random order. First, they experienced the original, then the left, and then the right. And when they're done with that first block, we were able to present the 3 conditions in another random order in a second block for trials 4, 5, and 6. So first they saw the right, then they saw the original, then they saw a left. In the next block of trials 7, 8, and 9, you see the same random order, but it just happened randomly that it was the same right, then original, then left. In the next block of 3 conditions, right, we did left, original, and right, and so on, and so on, and so on, until all 54 trials, 18 blocks, were completed. The only deal with block randomization is you have to complete a block of randomized trials before you go on to the next block, and within each block, the order of conditions is presented randomly. But every participant experienced all of these blocks, right? And each participant got a random order of those blocks. That's the first type of complete counterbalancing. The next type we call ABBA counterbalancing, and don't get that confused with the 70s pop sensation ABBA. In ABBA counterbalancing, every participant experiences first one order of conditions and then the reverse of that order. So ABBA is the simplest type of ABBA counterbalancing, where you first get condition A, then B, and then the same people who experience that order repeat the reverse of the order, first B and then A. But you can do it with more than 2 conditions. So you could have first A, then C, then B, and then you'd reverse that order, C, then B, then A. It's complete counterbalancing because every participant experiences multiple orders, and we'll contrast that with incomplete counterbalancing, and I'll give you 2 examples of that. Incomplete counterbalancing involves participants experiencing only one order of all of the conditions, but every participant experiences all the conditions. Different people get different orders, and in this way, the order effects are controlled for, because you can test to see if there were order effects. You can compare these different groups of people experiencing different orders, and if there's differences among them in terms of the order of their experience, you know you have a problem. The two methods of incomplete counterbalancing, where different people experience all conditions but in different orders, we call all possible orders. And the next is called the balanced Latin square. And that involves a small formula that I hope you'll be able to plug and play in lab. For all possible orders, every participant experiences only a single order, right? And each possible order must be represented. This is pretty easy when there's two conditions because there's only two orders, right? First A and then B. And then the other one is B and then A, so there's only two orders. For incomplete counterbalancing, different people would get A and then B, and then another group of different people would get first B and then A. It's not ABBA counterbalancing because that means everybody goes through both of those orders. For all possible orders, you'd have two different groups of people. One gets one order, the other gets the other order. You'll see that the more conditions we have, the more possible orders there are. So how many possible orders of three conditions are there? If you had A and B and C, well, there would be ABC, ACB, BAC, BCA, CAB, and CBA. There are 6 possible conditions. To find out how many possible, there's 3 conditions, there's 6 possible orders. To determine the number of possible orders, we use this formula that's written in factorial notation. And we read this as k factorial, where k is the number of conditions. K factorial is equal to k times k minus 1 times k minus 2 times k minus 3, and so on and so on and so on, until you get down to the number that is k minus 1, or if k is 3, then it's 3 minus 2 or 1 condition. That's the last number that you multiply by. The last number you multiply by is 1, right? So 3 factorial would be 3 times 2 times 1 equals 6, so there's 6. So what's 4 factorial? Well, it would be 4 times 3 times 2 times 1. 5 factorial would be 5 times 4 times 3 times 2 times 1. So 4 times 3 is 12, times 2 is 24, times 1 is 24. And 5 factorial is 5 times 4, which is 20, times 3 is 60, times 2 is 120 times 1. So if you want to have every possible order of 5 conditions experienced by different people, you need at least 120 people to participate in your study. So this incomplete counterbalancing method of all possible orders, it doesn't really make sense when you have more than 3 or 4 different conditions, because you'd have to have too many participants. There's so many orders. It would not be practical to use this method of counterbalancing for 6 conditions, for goodness sake. So for 4 conditions, it would be 4 times 3 is 12, times 2 is 24, times 1 is 24. You'd have 24 different orders of 4 conditions, and you need at least that many participants for all possible orders to be represented. The last type of counterbalancing also involves a formula. The last type of incomplete counterbalancing requires you to create what's called a balanced Latin square. However many conditions that you have, you form a square that is k by k orders by conditions in area. So you end up with a number of columns in your square that's equal to the number of conditions, and the number of rows in your square that is also equal to the number of conditions. For example, if you have 4 conditions, you would first put all the conditions into a random order, right? So D is number 1, B is number 2, A is number 3, and C is number 4. And then, once you have the random order established, you would follow this formula, and you'll have this on your formula sheet. The first row order formula goes 1, 2, and then K, then 3, then K minus 1, then 4, then K minus 2, and so on and so on. So how do you create the first row for 4 conditions? Well, let's follow the formula. k equals 4, so it'd be 1, 2, 4, then 3, and you stop, because that first row is only as long as the number of conditions that you have. If you have more conditions than 4, you can still use this formula. Let's say that we had 6. It'd be 1, 2, k equals 6, and then 3. 6 minus 1 is 5, and then 4, and then you stop because you're at 6. 1, 2, k, 3, k minus 1, 4 is 6. Stop making your first row, and then go down to the next row. The rest is easy. For the second and all remaining rows, just add 1 to the row above it. So if our first row was 1, 2, 4, 3, then the second row, and that we get that by following the formula, the second row would just be 1. You add 1, so you get 2. Add 1 to 2, and you get 3. Add 1 to k. Well, k was 4. If you add 1 to it, you get 5, but we don't have 5 conditions. So that's when we start over, with k plus 1 being equal to 1. So if the first row of 4 conditions is 1, 2, 4, 3, the second would be 2, 3, 1, 4, because you add 1 to k, you start over at 1. What would the second one be? What would the third row be? If the first row is 1, 2, 4, 3, and the second is 2, 3, 1, 4, the third row would be 3, 4, 2, and then for that last one, the second row, last column was 4, you add 1 to it, you'd start over again at 1. So, 2 things to remember. One is that this formula only works for even numbered squares. We're not going to learn the formula for odd numbered squares right now, or this semester, but this only works for even numbers of conditions. And I will only give you problems where there's even numbers of conditions. And the second is there's lots of videos on my YouTube channel that show you how to practice forming a balanced Latin square. We used it in an experiment that came out of Emory University back in 2006, and it had to do with female birds' responses to male bird song. And we had a lot of different songs from different male birds. We wanted each female bird to hear a different order of those songs. Here, k was 14, so we followed that formula. 1, 2, k, 3, k minus 1, 4, k minus 2, 5, k minus 3. And you can see that first row follows exactly that formula. 1, 2, 14 is k, 3, 14 minus 1 is 13, 4, 14 minus 2 is 12, 5, 14 minus 3 is 11, 6, 14 minus 4 is 10, 7, 14 minus 5 is 9, 8, and then we stopped that first row because that's 14 different conditions. Add 1 to each one of those columns to get the next row, and so on, and so on, and so on. And that's how we came up with 14 different orders of 14 different conditions in a perfectly balanced Latin square. Next, we're going to learn how to compare averages of these two different treatments when we do a repeated measures design. And we'll find that we're not actually working with 2 different averages. We're only going to be working with 1 average. And that's in the next video lecture on the repeated measures or related samples t-test. See you next time.